Hi. So now let us continue from where we left off. So there's a third lecture in the series, and now we begin with elementary matrices. What's an elementary matrix? There are three types of row operations. Remember, what are the three types of row operations? Exchanging two rows is one operation. Say exchanging the second row and the third row, if you like. That's an example of an elementary operation. Multiplying a given row by some non-zero number. So for example, I want to multiply the fifth row by 1 by 4. That's a elementary operation. Another important elementary operation is that adding to a given row a multiple of some other row. Ri prime equal to Ri plus Crj. These are the three basic examples of row operations. There are three. These are the three elementary row operations. Now, to each of these row operations, there corresponds an elementary matrix. So, what's an elementary matrix? Let us do the following. Let us consider the operation of multiplying the kth row by gamma. Let us look at the operation of multiplying the kth row by gamma. Gamma non-zero. So what you do is you start with the identity matrix. You start with the identity matrix of size m cross m. Start with the m cross m identity matrix and multiply the kth row of the identity matrix by gamma, and you call that matrix mk gamma. So we say that mk gamma is the elementary matrix corresponding to the elementary row operation, namely multiplication of the kth row by gamma. Now similarly, look at the elementary row operation of exchanging the ith and jth row. Now do this operation of exchanging the ith and the jth row to the identity matrix of size m cross m. Then the matrix so obtained will be called Pij. The matrix so obtained will be called Pij. So Pij is the elementary matrix corresponding to the elementary row operation of exchanging the ith and jth rows. Now you start with the identity matrix of size m cross m and perform the operation Ri prime equal to Ri plus Crj. That is adding to the ith row a multiple of the jth row. Here I should say I and j are not equal. Here notice that I and j should be different. Adding to the ith row, c times the jth row, j not equal to I. I did not write it in the slide. Please make a note of this. Okay. So you perform the same row operation on the identity matrix of size m cross m, and you get a new matrix. Let us call it EIJC. Exercise: take m equal to 4. Take 4 by 4 matrices and write down the elementary 4 by 4 matrices. Say, for example, write down E12 with E12C. Take I equal to 1, J equal to 2, E12C, and M 4 by 4 matrix. Start with a 4 by 4 identity matrix and write down E12C. Write down E23C. Write down E32C, etc. Write down MK gamma for various values of K. Write down P12, write down P43, etc. So write down these things explicitly so that you get an idea as to what are elementary matrices. Okay. Now there are some basic rules of matrix multiplication. You know the definition of matrix multiplication. The very first lecture, we saw the definition of matrix multiplication. Now let us look at the following problem. Let us consider the operation of, let us look at the following problem. Given a matrix A, how to pick out the jth column of A? Given a matrix A, how do I simply pick out the jth column? Is very simple. You simply compute AEJ cap. You simply compute AEJ cap. The product AEJ cap will be the jth column of A. What is EJ cap? EJ cap is a column vector with 1 in the jth position and 0 elsewhere. Standard unit vector. Standard column unit vector. A is a M cross N matrix. So EJ cap must be an N cross 1 matrix. Otherwise, the matrix product will not make sense. So in order for the matrix product AEJ cap to make sense, you want EJ cap to be the N cross 1 matrix. That's a stand with 1 in the jth slot and 0 everywhere else. AEJ cap picks out the jth column of A. Similarly, let fk cap be the standard row vector which has 1 in the kth slot and 0 everywhere else. So fk is a 1 cross m matrix. A is a m cross n matrix. So fka will be a 1 cross n matrix. What will it be? Fk cap A picks out the kth row of A. So you know how to pick out the jth column of A. You know how to pick out the kth row of A. You simply have to multiply on the right by EJ cap or multiply on the left by FK cap, as the case may be. These are the two basic rules. Exercise, verify rules 1 and 2. Do the actual matrix multiplication and check the correctness of these rules. Now comes rule number 3. This rule number 3 is the same as theorem 11 in the slides. Let me throw you theorem number 11 on the slides. Theorem number 11 on the slides is here. Yeah. This theorem 11 in the slide is written very algebraically. I want to slightly paraphrase it so that and write it more in colloquial terms. So, and that is rule number 3. So, what does the rule number 3 say? The rule number 3 is the same as theorem 11 in the slides. What is rule number 3? Performing an elementary row operation on A is equivalent to pre-multiplying the matrix A by the corresponding elementary matrix. Okay, one has to verify this. What are we supposed to verify? Let us try it for there are how many different elementary operations there are? There are 3 types of elementary operations, and so we have to make 3 verifications. Suppose I look at the elementary operation of exchanging the ith row and the jth row. Look at the elementary operation of exchanging the ith row and interchanging the ith row and the jth row. So take a matrix A, take a M cross N matrix A, interchange the ith and the jth row. Now take the same matrix A and multiply it on the left by Pij and compare the results. The result is the same. So performing the operation Ri exchanged with Rj is the same as computing Pij of A. Take another row operation. Adding to the ith row C times the jth row. J is not equal to I. Again, let me emphasize. Adding to the ith row C times the jth row. Perform this elementary matrix on perform this elementary operation on your matrix A. Also calculate the EIJC A. Also calculate EIJC. What is EIJC? You got this EIJC. Multiply EIJC and A. Take the product of EIJC and A. The product EIJC of A, the product EIJC is the same as adding to the ith row C times the jth row. Third rule, MK gamma. Suppose you take a matrix A and you calculate MK gamma times A. That matrix will be the same as the result is the kind of matrix that you will get will be the same as the matrix you would get when multiplying the kth row of A by gamma. Performing the row operation of multiplying the kth row by gamma, the same effect can be obtained by computing the matrix product mk gamma times A. So what do these things illustrate? These three things can be summarized as rule number 3. Performing an elementary row operation on a matrix is equivalent to pre-multiplying the matrix by the corresponding elementary matrix. Very, very important rule, rule number 3. Please check. Now we'll talk about prefactors. Now you may have a matrix equation. Suppose you got 4 matrices A, B, C, D. You got 4 matrices A, B, C, D, and suppose AB equal to CD. Suppose you got this matrix equation AB equal to CD. Then A and C are called the prefactors. A and C are called prefactors. B and D will be called post factors. Post factors we will never deal with in this course. We'll only deal with prefactors. Now suppose if E is an elementary matrix of the one of the 3 kinds, EIJC, MK gamma, or PIJ. E is any one of these 3 families of elementary matrices. What I can do is that I can multiply equation number 1 on the left by E, right? So I can, from 1 I can get EAB equal to ECD. But what is EA? Multiplying A on the left by an elementary matrix is the same as performing the corresponding elementary operation on A. Multiplying C on the left by E is the same as performing the corresponding elementary operation on C. So the new matrices are A prime and B prime. So from AB equal to CD, we get A prime B equal to C prime D. Equation 1 and equation 2 are completely equivalent. In other words, we get rule number 4. Okay, rule number 4. One may perform the same elementary operation. Remember, the same elementary matrix E on the left and E on the right. So EA and EC, EA is called A prime, EC is called C prime. So A prime can be obtained from A by an elementary operation. C prime is obtained from C by an elementary operation. Same elementary operation has to be performed on the prefactors A and C, and we get a new equation A prime B equal to C prime D. So rule number 4, one may perform the same elementary row operation on the prefactors in a matrix equation 1. In a matrix equation 1, one may perform the same elementary operations on the prefactors A and C. And we get a valid result is a valid matrix equation which is equivalent to the original matrix equation. Okay. So this is rule number 4. Please understand these rules very well, and these rules you must commit to memory. Write down the simple exercise, write down the inverse of the matrix. Remember, Pij, Mk gamma and Eijc are all square matrices of size m cross m. When is a square matrix said to be invertible? When is a square matrix A said to be invertible? A square matrix A is said to be invertible if there exists another square matrix B of the same size such that AB equal to I and BA equal to I. So then you say that a square matrix is invertible. Show that Pij, Mk gamma, Eijc are all invertible matrices by actually displaying their inverses. Very, very important exercise. Please work out this exercise in great detail, and it's very, very essential, and it will be very useful in the study of matrices. Now let us see. Okay, we have got these rules. Rule number 4. How to use rule number 4? How to use rule number 4? Rule number 4 can be used very, very effectively to compute A inverse. This is called the Gauss's method for computing A inverse. How to find the inverse of a square matrix? First of all, you don't know whether the square matrix has an inverse at all. The zero matrix doesn't have an inverse. So square matrices may or may not be invertible. So first of all, I give you some square matrix. As such, it's not clear to me that it is invertible. But the procedure we follow will do two things. Either it will tell you that the inverse doesn't exist, or it will tell you that the inverse exists and it will give you the inverse. So the story is complete. So the story will be complete. So let us take I'm going to explain this method through a simple example. What is the example I'm going to take? I'm going to take a 3 by 3 matrix. 1, minus 1, 2, minus 1, 2, 2, 2, 1, 2. So 3 by 3 matrix. I'm not sure whether it's invertible or not. Let us examine. So let us write, so A is a 3 by 3 matrix and I is the 3 by 3 identity matrix. I is the 3 by 3 identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So identity matrix has the obvious property that AI equal to IA. AI equal to IA. Is it a valid matrix equation? It's a perfectly valid matrix equation. What are the prefactors? The prefactors have been indicated in the equation. A and I are the prefactors. So we got a valid matrix equation and we got the prefactors. What does rule number 4 say? Rule number 4 says that we can perform the same row operation on the prefactors and you will get an equivalent valid matrix identity. So AI equal to IA. The idea is that on the left hand side, on the prefactor A, we'll keep on performing elementary operations and we'll perform the same elementary operations on the prefactor I in the same sequence. And we will try to reduce the left hand side A to I and the right hand side I will turn into some other matrix B. And so the final equation will read I equal to BA. I equal to BA, and that B is the inverse of A. That's the idea. So I want to reduce this matrix A to the identity matrix. So your original A is here. So from this A, by performing row operations, I must get I. How to do that? R2 prime equal to R2 plus R1. That will kill the 2, 1 entry. This minus 1 will now become a 0. R3 prime equal to R3 minus 2R1. That will kill the 3, 1 entry and make it 0. So these are the two row operations I must perform in succession. The same row operations in the same order I must apply on the prefactor I, and I'll get a new matrix equation. What is that new matrix equation? The new matrix equation is going to be 1 minus 1 2. That's okay. And the second one, there's going to be 0 here and there's going to be 0 here. I'm going to add, right? I'm going to add to the second row the first row. So I'm going to get 1 and I'm going to get 4. That's exactly what I'm getting. And similarly for the third row, you can just check. And the same operations in the same order, mind you, are being applied on the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And we get this new equation I'm getting. All right. Now what is the next thing to do? I must make this entry. I must make the 1, 2 entry 0. How do I do that? R1 prime equal to R1 plus R2. That will kill this minus 1 and make it 0. And then R3 prime equal to R3 minus 3R2. That will make this 3. That will kill the 3, 2 entry and make it 0. And I must perform the same operations in the same order on the prefactor that you see on the right hand side. Perform it and you get 106, 014, 00 minus 14. On the right hand side, you get 210, 110 minus 5 minus 3, 1. Okay. Now, what am I going to do? This 3, 3 entry should become 1. How will the 3, 3 entry become 1? The row operation I perform is R3 prime equal to minus 1 by 14 R3. Perform the same row operations on the prefactors. You get 106, 014, 001, and then I is just being copied as it is. The right hand side is 5 upon 14, 3 upon 14 minus 1 by 14. Now you have to make this 1, 3 entry, and the 2, 3 entries must become 0. So what row operations? R1 prime equal to R1 minus 6 R3. R2 prime equal to R2 minus 4 R3. That will make the left hand side empty. So R1 prime equal to R1 minus 6 R3, R2 prime equal to R2 minus 4 R3 will make the left hand side I, and the right hand side you get some matrix. And this matrix you have to do the algebra, by the way. You have to do the calculations, and you get this ugly matrix has 1 by 14, 1 by 14 all over the place. This 1 by 14 has been taken out common. It looks more neater. Minus 2, minus 4, 6. Minus 6, 2, 4. 5, 3, minus 1. And so this is your matrix B. Your B is basically A inverse. It is 1 by 14 times this matrix. Inverse has been computed. Now suppose, for example, in this process, it happens that one of the rows on the left hand side becomes 0, 0, 0. Suppose in the process at some stage we get that all entries in a row are 0, then the conclusion is that A inverse doesn't exist. How do you prove this? Exercise, prove this, or wait for a little while. After a few lectures, it will become automatically clear to everybody. I think let us stop this lecture. Let us stop this lecture 3A, and we will continue this later.